Hi everyone, I'm Gengtao Xu. I'm a master student from Boston University.
I'm Jing, also from Boston University.
I'm Runqi Tian.
Before we discuss some more details, let's take a look at the overview. The framework we use is Apache Flink, which is a really powerful and easy to use. In this grand challenge, the problem we need to address is to detect anomaly events for data streams, something like unstable current. Before we starting to design our algorithms, we need to analyze the original data and do some pre-processing work on it. Compared to the naive strategy, our parallel strategy is very accurate and fast. The accuracy is rank 1 and the total runtime is rank 3. Then, in time analysis, we will prove why our parallel strategy is always faster. During this grand challenge, we did meet a lot of challenges. We will discuss them and give our conclusion and future work in the end. Now, let's discuss the framework we used, Apache Flink.
Let me introduce Flink. Flink provides us abundant APIs for data streaming. These APIs are really easy to use, and when we use these APIs, we do not need to worry about the low-level implementations. Well, one of the most important features of Flink is watermark. In query 2, we have to deal with late data. In this case, watermark would be really useful. Flink also provides us window operation, which allows us doing computation within a range of data. We use window frequently in our implementation. Finally, the best thing I like about Flink is that it can manage parallelism automatically. If we want to change the parallelism number, we don't need to modify our code. All we need to do is set it up in just one line of code.
So let's firstly see the data. We firstly look into the data and trying to find out some basic characteristics. As we can see, the data represents the value of voltage and the current by time. Every 1,000 input tubes correspond to the readings for 1 second, which is 1,000 milliseconds. The figure shows samples of few seconds readings. Each line of different colors correspond to 1 second's data. So as shown in the figures, we find that in every second, the data changes regularly with a tiny phase differences. This inspired us to deal with the lost data. We firstly think we may fit in the function to complete the lost data. The native strategy for queries process the input stream in a sequential way. Input tubes is firstly gathered by window 1 and extracted the features. Then each new pairs of features is added to window 2, and window 2 will apply the DEBS scan algorithm, which contains a forward and a backward path, and as shown in the figure. The event detection process is time-consuming due to it has a lot of processes, such as updating cluster structure and the whole backward path. Apparently, it is unnecessary to wait for processing features while new features is continuous inputs. So we implement a parallelized strategy in our solution. The basic idea of our parallel solution is to divide the single thread process into partitions, apply events prediction on each partition, and then merge the result, which is a divide and conquer strategy. And finally, we verify the result and output them.
Let me introduce our parallel strategy in detail. This figure shows our parallel strategy. Stage 1 represents the pre-processed data stream. It is waiting to be processed in parallel. Our strategy divides stage 1 data stream into 2,000 sized partitions, and the adjacent partitions overlap each other. The overlapping part contains 100 elements. Next, we execute naive algorithm on each partition and generate results. Then we need to merge results generated by each partition. We use the last 100 elements in the first partition to replace the first 100 elements in the second partition. For example, when we want to merge partition 1 and partition 2, we use the last 100 element in partition 1. Then we generate results which is shown in stage 3. This result still contains many errors. Next, we will verify the results to improve the accuracy.
As we said before, unfortunately, the merge results sometimes could be wrong. There are two cases that might be happen. Case 1 is a false positive, which means that we detected an event, but it isn't. Case 2 is an event that we missed. Both of them are caused by the wrong window start position during parallel strategy. There are two cases can affect the window start position. First, when we detected an event, we clear the window contents, and the new window start position is where the previous event is detected. And second, when we do not detect an event after processing more than 100 features, which is the window size, the algorithm simply clears the window, and in single-thread algorithm, we're good. However, in the data parallel algorithm, each task cannot know where other tasks have possibly detected an event, and hence cannot know the previously detected event information. Each task starts its window from where its partition starts, and this position can be different from the window start position in the single-thread one. Therefore, to address this problem, we need to correct our window start position by running event detection again from the corrected window start position, and then recheck the detected events to make sure they are not false positives, and can also avoid missing events, since at this moment, if there are some events are missing in the previous detection, they can definitely be detected during this time. And now let me analyze the time. For naive strategy, basically only need to process one feature after each data request, after each data request. Hence, the overall runtime is n times t plus t data, where n is a number of batches, t is the processing time on one feature. But for the parallel strategy, we can process multiple features simultaneously. However, due to the single-thread data source, each thread needs to wait t data time for starting process, and need t and v time for merging and verifying in each parallel processing block. The overall runtime is n divided by p and times t and p, where p is parallelism and t and b is time for each parallel processing block. To prove that our parallel strategy, we assume that t greater than tmv and t also greater than t data, which is reasonable, and we derived an inequality which always holds, which means our parallel strategy is always faster than the naive one. Next, we will discuss some challenges we met during this challenge and give some solutions.
We faced many challenges while designing our strategy and implementation the parallel algorithm. The first one is to transforming the prediction algorithm into stream processing. We firstly try to divide the processing logic of event detector into separate parts, so as Flink operators. However, the water flow of the event detector is highly complex. So we decide to make the whole algorithm inside a single operator and focus on our optimization efforts on other parts. The second challenge we meet is the efficiency of result verification. As the verification stage needs to wait a few events for correcting the results. The stage must be processed after parallel processing. We improved our verified stage for a balance of time consumption and accuracy. And the next challenge is to deal with the late data. In Create 2, we may facing the late data and also the lost data. We leverage the Flink's support of event time and watermarks. And watermarks makes it possible to arrange the late data with a trade-off of a little latency, but highly improves our accuracy. And the last one is to handle the lost records. We initially trying to find an algorithm to simulate the lost record. However, the current data is hard to fit as a function. So we noticed that the data shows regularly in each time unit. So we complete the lost data with the previous data of the same period. As shown in the figure, we copy the history data to complete the lost data. We believe this is a good way since we cannot extract the event in lost data, and the features of the lost data is singular.
That's all about our algorithm. Our algorithm achieves almost the same accuracy as the sequential model and has a much faster speed. However, there is still some imperfections in our method. For example, watermarks can help us dealing with the late data in Query 2, but it can also increase the latency. In Query 2, we set a 20-second latency to catch all late data. But this is unnecessary when the data quality is good. We can improve the latency by setting up a heuristic watermark. For example, when the algorithm detects many data arrives late, the heuristic watermark will increase its latency. It will also decrease the latency when the stream quality is good.
That's all. Thank you.